In the quiet darkness beyond the solar system, storms unfold on worlds that never show their faces. No camera sees their clouds, no probe tastes their winds. The only evidence is starlight that dims, shifts, and returns with a steady rhythm. From these small changes, astronomers infer jet streams that race around giant planets, night sides where rock and metal can condense, and high hazes that hide entire weather systems beneath a soft veil. The universe keeps these storms distant and silent, yet their signatures remain written in light, measured with patience, and translated into calm. Physical stories of heat, motion, and matter. If this kind of slow, science-based journey helps with sleep, study, or quiet focus, support the channel with a like and subscribe. New space documentaries arrive regularly, with gentle pacing and grounded explanations, built to let the mind settle while the cosmos continues moving. Across the Milky Way, planets circle stars that appear as single points of light. From this distance, an exoplanet is not seen as a disk with clouds and continents. It is sensed as a small change in a star's brightness, a slight wobble in a star's motion, or a faint reshaping of starlight that passes through thin air at the edge of a far-off world. The study of storms on these planets begins in that indirect realm, where weather must be reconstructed from signals that are incomplete and often ambiguous. Observations indicate that storms are not identified by a single unmistakable signature. They emerge from repeated measurements, careful comparisons, and models that respect physics while admitting what cannot yet be measured. One common path to an exoplanet is the transit, when a planet crosses in front of its star and briefly blocks a fraction of starlight. The dip in brightness can be small, but it repeats with the planet's orbit. Over time, that repeating dip establishes a planet's size and the rhythm of its year. In some systems, the dip is not perfectly smooth. The star itself can vary, and instruments can drift. Yet when the data are stable enough, small differences appear from one transit to the next. Those differences can hint at changing conditions around the planet, including clouds and hazes that alter how the planet hides the star. A storm is not seen directly, but a changing veil around the planet can leave a trace in the light curve, as if weather briefly thickens the planet's silhouette. Another path is radial velocity, where a star's light shifts slightly in wavelength as the star moves toward and away from the observer under a planet's gravitational pull. This technique is less about storms and more about confirming a planet's mass. Yet mass matters for weather because it sets gravity, and gravity influences the height of an atmosphere and the speed at which gases mix. A low-gravity planet can have an atmosphere that extends far outward, where sunlight can more easily sculpt it. A high-gravity planet can compress air into denser layers where clouds form under different pressures. The motion of the star becomes a foundation for later reasoning about climate and storms, even when it cannot describe clouds by itself. Once a planet is known to transit, its atmosphere becomes accessible in a special way. During a transit, a small fraction of starlight filters through the planet's limb, the thin ring of atmosphere around the planet's edge. Molecules and tiny particles in that air absorb and scatter specific wavelengths, imprinting a spectrum that differs slightly from the star's own. This is transmission spectroscopy. In the clearest cases, it reveals water vapor, sodium, potassium, carbon monoxide, carbon dioxide, and other gases. In many cases, the signature is muted or flattened. Observations indicate that high-altitude hazes and clouds can hide deeper layers, washing out molecular features. That flattening is one of the earliest ways storms enter the story. If clouds are widespread and steady, the spectrum remains consistently muted. If clouds are patchy or variable, the spectrum can change with time, suggesting weather patterns that shift across the limb. A planet also emits and reflects light, and that light can be separated from the star's signal in subtle ways. When a planet orbits its star, the visible portion of its dayside changes, much like phases of the moon. As the planet moves, the combined light of star and planet brightens and dims by a tiny amount. This is a phase curve. In infrared wavelengths, phase curves can reveal the distribution of heat across a planet's surface and atmosphere. A planet with efficient winds can carry heat from the day side to the night side, smoothing temperature differences. A planet with less redistribution can keep its heat concentrated under the star. Storms are inferred when the phase curve shows irregularities, shifts, or time variability beyond what a simple, steady circulation predicts. The data suggests changing cloud cover or changing patterns of heat transport, both consistent with dynamic weather. Eclipses add another window. When a transiting planet passes behind its star, its own emitted and reflected light temporarily disappears. This secondary eclipse allows observers to measure the planet's contribution by subtraction. In infrared, it can estimate dayside temperature and sometimes identify gases by their spectral fingerprints. In visible light, it can measure reflectivity, which can be enhanced by bright clouds. A highly reflective dayside can indicate thick cloud decks or hazes that scatter starlight. If the measured reflectivity changes over many eclipses, that variability can point to evolving cloud patterns. It remains uncertain, in many systems, whether such variability is driven by storms, by slow climate shifts, or by instrumental and stellar effects that are difficult to separate at very low signal levels. The cautious approach is to treat variability as a clue that demands repeated observation, rather than as proof of a specific type of storm. Direct imaging offers a different style of evidence, though it is rare and technically challenging. It aims to block the star's glare so that the planet's own light can be seen. The planets that are most easily imaged tend to be young, massive, and far from their stars, still glowing from the heat of formation. Their spectra and brightness can vary as they rotate, implying patchy clouds. These objects sit at the boundary between giant planets and brown dwarfs, and their study provides an important analogue for exoplanet storms because rotation turns cloud patterns into measurable brightness changes. When the brightness rises and falls with rotation, it suggests that cloud bands and storm systems cover some longitudes more than others. The timescales of change can be hours to days, set by rotation and by the movement of cloud features. The physics resembles weather on a giant planet, but the compositions and temperatures can be far stranger than those found in the solar system. Even without direct imaging, rotation can sometimes be inferred. Small periodic signals in phase curves or in spectral line broadening can hint at how fast a planet spins. Rotation matters because it shapes atmospheric circulation, organizing winds into jets and vortices. When rotation is fast, the Coriolis effect becomes strong and can produce bands and long-lived structures. When rotation is slow or locked to an orbit, circulation can take on a stark day-to-night pattern. In the distant outer layer of inference, storms are not yet named or described as swirling clouds seen from above. Instead, storms appear as consequences of rotation and energy flow, visible only through changes in light. The star's own behavior complicates all of this. Star spots, flares, and magnetic activity can mimic or obscure planetary signals. A planet transiting across a dark star spot can make the transit appear shallower for a moment, producing bumps that look like changes in the planet. stellar faculae, brighter regions, can also distort the baseline. Careful analyses model the star and seek consistency across wavelengths and across time. When a pattern appears only at one wavelength, it may be atmospheric. When it appears across all wavelengths in a way consistent with stellar activity, it may belong to the star. The boundary between weather and noise is part of the science, and it shapes what can responsibly be claimed. Instrument limits also set the pace. Many measurements involve differences of only a few parts per million of starlight. Observations require stable detectors, repeated transits, and careful calibration. Space telescopes reduce the interference from Earth's atmosphere, but they still face thermal drifts and subtle systematics. Ground-based telescopes can contribute with large mirrors and high-resolution spectroscopy, but Earth's air adds absorption that must be corrected. Storm inferences often rely on trends that persist across instruments and methods. When multiple lines of evidence converge, confidence rises. When evidence is thin, uncertainty is stated plainly. In this outer region of the topic, the strangest exoplanet storms are still shadows cast in starlight. The data do not show lightning bolts, towering clouds, or rain sweeping across a horizon. They show a curve that shifts, a spectrum that flattens, a hotspot that moves, or a brightness pattern that repeats with rotation. From these distant signals, scientists build cautious pictures of atmospheres that are active rather than static. The first lesson is that exoplanet weather is measured as a difference, not as a photograph. It begins as faint light that refuses to stay perfectly steady. A planet's storms do not begin inside its clouds, they begin in the architecture of its orbit. The distance to the star sets the energy arriving at the top of the atmosphere. The shape of the orbit sets whether that energy is steady or pulsed. The planet's tilt sets how seasons play across latitudes. In the most extreme cases, the orbit and the star's gravity reshape the planet's rotation itself, forcing the same face to look toward the star at all times. Observations and theory agree that this condition, tidal locking, is common for planets that orbit close to small, cool stars and also for many giant planets pressed tightly against hotter stars. In those systems, the stormiest weather is expected not as a mild variation around a global average, but as a response to a permanent division between day and night. Tidal forces arise because gravity is stronger on the near side of a planet than on the far side. The difference stretches the planet, raising bulges. If the planet rotates at a different rate than it orbits, those bulges are dragged out of line with the star. The star's gravity pulls them back, and the resulting torque acts like a brake. Over time, rotational energy is dissipated as heat inside the planet, and the rotation slows until the planet's day matches its year. The result is synchronous rotation, where one hemisphere experiences continual daylight and the other hemisphere lies in continual darkness. The timescale for reaching this state depends on distance, planet structure, and internal dissipation, but for close-in planets it can be short compared to the age of the system. The geometry becomes a climate engine. It creates a permanent day side where air is heated, and a permanent night side where air cools. The contrast drives winds. Warm air expands, becomes less dense, and tends to rise. Cool air contracts, becomes denser, and tends to sink. On a tidally locked planet, rising tends to dominate near the point beneath the star, the substellar point, while sinking tends to dominate on the night side. This establishes a large-scale circulation that moves air from day to night in the upper atmosphere and returns it from night to day at deeper levels. If the planet has an atmosphere thick enough to transport heat, this circulation can prevent the night side from becoming too cold and the day side from becoming too hot. If the atmosphere is thin, or if gases escape, the day-night contrast becomes sharper, and winds can become more intense in the regions where air accelerates across the terminator, the ring of twilight between day and night. The same geometry influences clouds. Condensation depends on temperature and pressure. On a tidally locked world, a condensable substance can vaporize on the day side and condense on the night side. This can create a planetary scale cycle where material is carried as vapor into darkness, condenses into particles or droplets, and falls, only to be returned as vapor when circulation brings it back to daylight. The substance can be water on cooler worlds, but on hotter worlds it can be silicates or metals. Even before any specific cloud chemistry is considered, the orbit outlines where clouds might form and where they might disappear. The storms become, in part, a geography of condensation shaped by starlight. Close orbits also invite intense tides that do more than lock rotation. They can heat a planet's interior by flexing it. In the solar system, tidal heating is seen in moons such as Io, where gravity from Jupiter and orbital resonances keep the orbit slightly elliptical, causing constant flexing and volcanic activity. For exoplanets, similar heating can occur if the orbit is not perfectly circular or if the planet experiences gravitational pulls from companions. Internal heat can rise into the atmosphere and influence weather, even when the planet is a gas giant without a solid surface. Tidal dissipation can warm deep layers and change the flux of heat rising upward. Observations indicate that some close-in giant planets have inflated radii, larger than expected from their mass and age, suggesting extra internal heating. It remains uncertain how much of that heating comes from tides, how much from stellar irradiation interacting with atmospheric winds, and how much from other processes. The consequence for storms is that energy sources can be both external and internal, and the relative balance can vary widely. Orbital shape adds another dimension. A circular orbit delivers nearly constant average starlight. An eccentric orbit, stretched into an oval, delivers strong pulses at closest approach and weaker input when far away. When the planet swings close, the atmosphere can heat rapidly, then cool as the planet retreats. The heating and cooling can drive transient winds and changing cloud patterns. For planets with significant atmospheres, the response can lag behind the changing input because air and oceans store heat. Inference from phase curves suggests that some planets show measurable offsets between peak heating and closest approach, consistent with atmospheric heat capacity and transport. These systems imply storms that are not steady features, but episodes tied to orbital position. A close orbit also brings a planet into stronger stellar wind and more frequent flares, especially around active red dwarf stars. Energetic particles and ultraviolet radiation can alter the upper atmosphere, changing chemistry and heating. This can influence the formation of hazes and the rate of atmospheric escape. It can also affect the conductivity of the upper atmosphere, which may matter for lightning-like discharges and magnetically influenced winds. While the details remain uncertain, especially for smaller rocky planets, the broad picture is stable proximity to the star forces the atmosphere to respond not only to light and heat, but also to particle environments that are harsher than those experienced by Earth. Rotation, even when locked, still shapes storms through the Coriolis effect, the apparent deflection of moving air due to rotation on a synchronously rotating planet. The rotation rate equals the orbital period. Many close-in planets have short periods, so their rotation can still be rapid. In that case, air moving from day to night can be deflected into strong jets rather than flowing straight across. Models show that an eastward jet can form at the equator, shifting the hottest region away from the substellar point. Observations of some hot Jupiters match this expectation, with infrared phase curves showing the hottest spot shifted eastward. The jet itself can be a storm track, a channel of high-speed wind where waves and instabilities create variability. When rotation is slower, circulation can be more direct, with a large day-to-night flow and less banding. For planets not fully locked, the interplay becomes subtler. A planet may be in a resonance where it rotates a whole number of times for each orbit, creating repeating patterns of heating rather than constant day and night. Mercury in the solar system is in such a resonance. For exoplanets, resonances are possible, though harder to confirm. In those cases, the day-night boundary migrates, and the atmosphere experiences periodic heating cycles. Storms can then be shaped by a moving pattern, creating regions of repeated condensation and evaporation. The orbit also determines whether a planet sits within a star's habitable zone, where temperatures might allow liquid water under some atmospheric conditions. Yet even in that zone, tidal locking around small stars is common, and the weather may be dominated by the day-night contrast rather than by gentle seasonal shifts. For a rocky planet, the presence of oceans, continents, and ice would add complexity. But the outer layer of reasoning remains the same. Geometry sets gradients, and gradients drive motion. In this region of the story, storms are not yet described by their ingredients, but by their scaffolding. The planet is defined by where it receives heat, how fast it spins, how its atmosphere can carry energy, and whether tides add internal warmth. These strangest exoplanet storms begin as a consequence of this arrangement. They form in the permanent glare of a fixed day side, in the long cold of a fixed night side, and along the narrow ring between them where air is forced to accelerate and transform. Above the cloud tops and above the layers where most of an atmosphere's mass resides, there is often a region where the air grows thin enough that individual atoms and molecules begin to behave less like a dense fluid and more like a sparse gas. In this uppermost realm, sunlight does not merely warm the air. High-energy radiation can split molecules, strip electrons, and turn parts of the atmosphere into a weak plasma, a gas of ions and free electrons. For planets that orbit close to their stars, especially close to active stars, this upper atmosphere can become a place of continual disturbance. The boundary between a storm and a steady outflow grows less clear, because the dominant motion can shift from circulating winds to escape into space. The energy that drives this region arrives mainly as ultraviolet and X-ray radiation. These wavelengths are absorbed high in the atmosphere because they interact strongly with atoms and molecules. When absorbed, they deposit energy that heats the gas and creates ions. Heating increases the scale height, the vertical distance over which air pressure falls by a fixed factor. A larger scale height means the atmosphere puffs outward, extending farther from the planet. In some close-in gas giants, observations indicate a swollen upper atmosphere that absorbs starlight in ultraviolet lines, suggesting hydrogen extending to great distances. In some systems, a comet-like tail of escaping gas is inferred from asymmetric transit signatures, where absorption begins before the optical transit or persists after it. These features suggest that the upper atmosphere is being shaped by stellar radiation and wind, producing a flow that is not a simple weather pattern confined to the planet. Escape can take several forms. The simplest is thermal escape, where particles in the high tail of the speed distribution exceed the planet's escape velocity. For light gases, especially hydrogen and helium, this can be significant at high temperatures. More dramatic is hydrodynamic escape, where intense heating drives a bulk flow of gas outward, like a planetary wind. In hydrodynamic escape, the upper atmosphere expands and accelerates, carrying gas away in a continuous stream. This is most plausible for low-density planets or strongly irradiated ones. It remains uncertain for many planets exactly how strong the escape is, because observations must interpret limited spectral lines and separate planetary absorption from stellar variability. Still, the broad phenomenon is supported by multiple detections of extended atmospheres, particularly in ultraviolet observations of hydrogen and in some cases helium in near-infrared lines. For storms, the key is that the upper atmosphere is both a boundary layer and a driver. It can influence how energy enters the deeper atmosphere. If high-energy radiation is absorbed above the clouds, it can heat and expand the upper layers, changing the vertical temperature profile. This profile influences stability, the tendency of air to resist or encourage convection. A warm upper layer can cap convection below, limiting the rise of storm plumes. Alternatively, if heating creates strong temperature contrast between day and night at high altitude, it can drive fast winds that shear the tops of clouds and alter how aerosols are transported. The upper atmosphere can also host waves, including gravity waves that propagate from below and deposit momentum when they break, shaping winds and possibly contributing to variability. Ionization introduces new forces. In a partially ionized gas, charged particles can interact with magnetic fields. Many giant planets are expected to have magnetic fields generated by internal dynamo action. For hot planets with partially ionized upper atmospheres, magnetic effects can influence wind patterns. Charged particles moving across magnetic field lines feel a force that can resist motion, acting like a drag. This can alter the speed and direction of high-altitude winds, potentially changing the distribution of heat. In some models of very hot Jupiters, magnetic drag can slow winds and reduce the eastward shift of the hottest region. Observations of phase curves across different planets show a range of hotspot offsets, suggesting that multiple factors, including magnetic effects, may be at play. It remains uncertain how strong these effects are in specific cases, because magnetic field strengths are difficult to measure directly for exoplanets. Stellar wind adds another layer. Stars continuously emit a stream of charged particles. Close to the star, this wind is denser and faster. When it encounters a planet's upper atmosphere and magnetic field, it can compress the day side and stretch the night side into a tail. This interaction can create a bow shock ahead of the planet. If the shock and associated material absorb starlight, they can produce early ingress signatures in ultraviolet or optical measurements. Such signals are subtle, and alternative explanations exist. But the concept is physically grounded in plasma interactions known from solar system planets. In this view, the planet's upper atmosphere is not simply responding to starlight, but to a continual flow of particles that can vary with stellar activity. Variability in stellar wind conditions could translate into variability in the extent and shape of the upper atmosphere, adding another dimension to what might be called weather, though it is weather at the edge of space. Chemistry in this region is driven by light. Photochemistry, chemical change initiated by photons, can create and destroy molecules rapidly. Water vapor can be split into hydrogen and oxygen. Methane can break down into more complex hydrocarbons. Sulfur-bearing species can shift between forms. The products can form aerosols, tiny particles that create hazes. Hazes can rise high and spread widely, affecting how the planet reflects and absorbs light. Observations of some sub-Neptunes and hot Jupiters show spectra that are flatter than expected, consistent with high-altitude hazes. The haze itself can be part of a storm system if it is produced in localized regions and then transported by winds, creating patchiness. Yet the same haze can also be global and persistent, masking variability. In many cases, it remains uncertain whether a muted spectrum indicates thick clouds, photochemical haze, high metallicity, or a combination of these factors. Temperature contrasts at high altitude can be extreme. On a tidally locked planet, the upper atmosphere above the day side can be heated intensely, while the night side remains cooler. Because air is thin, radiative timescales can be short, meaning the gas can cool quickly when it moves into darkness. This can create sharp gradients along the terminator. Winds may accelerate as they respond to these gradients, leading to jets and shear layers. Shear can generate instabilities that mix air and move aerosols. In a deep, dense atmosphere, storms are often associated with convection and cloud formation. In the upper atmosphere, storms can be associated with waves, shears, and flows that change the planet's extended shape in starlight. Helium provides a specific example of how this region can be studied. In some planets, helium absorption at a near-infrared wavelength has been detected during transit, indicating a metastable helium population in the upper atmosphere. This line can trace escaping gas and can sometimes reveal velocities through Doppler shifts. Measurements suggest outflows that can be shaped by stellar wind and radiation pressure. The outflow can vary with time, potentially changing transit depth in that line. Such variations are difficult to confirm and interpret, but they illustrate a broader point. High-altitude storms may appear not as cloud changes, but as changing escape signatures, as the planet's upper air breathes outward and streams away. The upper atmosphere also connects to deeper layers through energy deposition. When particles from the stellar wind precipitate along magnetic field lines, they can heat the upper atmosphere and produce auroral emissions. Direct detection of exoplanet aurora remains challenging and uncertain, but the processes are well established in the solar system. If such heating occurs, it can alter temperature and winds at high latitudes, potentially influencing circulation patterns below through wave coupling. In this region, the strangest storms are storms of the boundary itself. They are the swelling and reshaping of a planet's outer air under radiation and particle flow. They are the creation of hazes that float high above clouds. They are winds that may be slowed by magnetic forces or driven into new patterns by day-night contrasts. They are also losses, as the planet's atmosphere escapes and trails behind. The evidence arrives as extra absorption in ultraviolet or helium lines, as asymmetries in transit timing, and as spectra that reveal a high, persistent veil. The observations indicate activity. They also demand restraint, because the same signals can arise from multiple causes. What is known is that, for many close-in planets, the top of the atmosphere is not calm. It is a frontier where starlight and space weather continually disturb the air, and where the distinction between meteorology and erosion can fade. When a giant planet orbits so close to its star that its year lasts only a few days, the star's heat floods the planet's dayside with an intensity that has no parallel among the giant planets of the solar system. These are the hot Jupiters. Many are expected to be tidally locked, with a permanent day side and a permanent night side. In that setting, the atmosphere becomes the main pathway for moving energy, and the winds can become the defining feature. The evidence for these winds does not come from watching clouds race across a disk. It comes from the way heat is distributed, from how the brightest region shifts around the planet, and from the way spectral lines are broadened or displaced by moving gas. Within this region of the topic, The storm is expressed as global-scale jet streams and fast circulation patterns that wrap the planet. Infrared phase curves are one of the clearest tools. A phase curve tracks how the combined light of star and planet changes as different longitudes of the planet rotate into view. If the planet re-radiates energy immediately where it is received, the brightest point should align with the point directly beneath the star. Yet observations of several hot Jupiters show the brightest region shifted eastward. This eastward offset indicates that winds carry heat from the day side toward the evening side, transporting warmth before it can radiate away. The magnitude of the offset and the contrast between day and night temperatures provide constraints on wind speed and on how efficiently the atmosphere redistributes energy. The data indicate that some hot Jupiters have strong day-to-night transport, while others retain a sharper contrast. The differences are consistent with variations in temperature, composition, and possibly magnetic effects, as well as with differences in cloud and haze distribution. The winds implied by these offsets can be immense. In models, the dominant feature is often an eastward equatorial jet, a band of rapid flow that circles the planet. The jet forms because the dayside heating drives rising motion near the substellar point, and the resulting waves and circulation patterns converge momentum toward the equator. The Coriolis effect organizes the flow, and the outcome is a super-rotating jet, meaning the atmosphere at the equator moves eastward faster than the planet's rotation. This jet shifts the hottest region eastward and can also produce broad temperature gradients between equator and higher latitudes. A hot Jupiter storm, in this view, is a persistent planet-encircling current of air that can reach kilometers per second in speed. High-resolution spectroscopy provides another line of evidence. When molecules in an atmosphere absorb starlight or emit infrared light, they produce spectral lines at known wavelengths. If the absorbing or emitting gas is moving toward or away from the observer, those lines shift slightly due to the Doppler effect. By measuring these shifts during transit or eclipse, observers can infer wind patterns. For some hot Jupiters, measurements suggest winds flowing from the day side to the night side along the terminator, producing blue shifts or red shifts depending on geometry. In other cases, line broadening suggests high-speed motion and rotation. These methods are challenging and rely on combining many lines to build signal, but they offer a direct handle on atmospheric velocities rather than relying solely on heat maps. Storminess on hot Jupiters is also reflected in variability. Repeated phase curve observations sometimes reveal changes in amplitude or shape. Variations can arise if clouds form and dissipate in different regions, changing how infrared light escapes. They can also arise if the circulation pattern itself shifts, perhaps due to instabilities in the jet or changes in the balance between radiative heating and dynamical transport. Models suggest that jets can develop waves and eddies that migrate, altering the distribution of temperature in clouds. It remains uncertain how common large temporal variability is, because many planets have limited repeat observations and stellar noise can interfere. Still, the growing set of multi-epoch measurements suggests that at least some hot Jupiter atmospheres are not perfectly steady from one orbit to the next. Clouds complicate interpretation but also enrich it. At very high temperatures, many condensates cannot form on the day side, yet they may form on the night side where temperatures drop. This can create a stronger symmetry in cloud cover. If clouds are present on the cooler morning side or night side, they can reflect starlight in the visible and block infrared emission from deeper, warmer layers. This can shift the apparent hotspot and change the phase curve. A planet can appear to have a different heat distribution not because heat transport changes, but because the level from which infrared light escapes changes with cloud cover. In that case, the storm includes not only winds, but also moving cloud boundaries that change the planet's effective photosphere, the layer from which most observed radiation emerges. The vertical structure matters as well. Hot Jupiter atmospheres can have temperature inversions, where temperature increases with altitude over some range, often due to absorption of stellar radiation by molecules or aerosols. An inversion changes where emission lines form and how efficiently the atmosphere cools. It can also affect stability, influencing whether air parcels rise and form deep convection. Many hot Jupiters likely have weak convection in their upper atmospheres because strong irradiation creates stable layers. Yet deeper down, where stellar heating is less dominant and internal heat can matter, convection can occur and feed waves upward. The jet streams in the upper atmosphere can interact with these waves, creating patterns of oscillation and variability. Chemical timescales add another dimension. On the day side, high temperatures can favor carbon monoxide over methane and can alter the abundance of other species. On the night side, cooler conditions can favor different chemical equilibria. If winds move air quickly between these regions, the chemistry can be in a disequilibrium state, meaning compositions reflect transport rather than local temperature alone. Observations indicate that some hot Jupiter spectra show signatures consistent with disequilibrium, though the details remain debated due to degeneracies with clouds and metallicity. In the context of storms, disequilibrium chemistry is a tracer of fast circulation. It suggests that air moves on timescales shorter than chemical conversion, preserving a memory of where it has been. Some of the strangest aspects of these storms are their scale and persistence. On Earth, jet streams are narrow bands compared to the planet's radius and are shaped by continents and seasonal shifts. On a hot Jupiter, the jet can span much of the equatorial region and remain anchored by the unchanging stellar heating pattern. The planet's atmosphere becomes a machine that continuously converts dayside heating into motion and motion into heat redistribution. The storm is not a transient event that builds and passes. It is a steady regime of extreme winds, with embedded variability, driven by a permanent day-night forcing. At the same time, the regime can change with temperature. As irradiation increases, radiative timescales shorten and the atmosphere can lose heat quickly. This can reduce the ability of winds to smooth day-night contrasts. Some of the hottest planets show smaller hotspot offsets and larger day-night temperature differences. This trend is consistent with the idea that, in very hot atmospheres, energy is radiated away faster than winds can move it. Magnetic drag may also become stronger as ionization increases. In that limit, storms may become more localized around the substellar region, and the equatorial jet may weaken. Within this region, the storm is defined by motion on a planetary scale. It is inferred from shifting hotspots, Doppler-shifted spectral lines, and variable phase curves. It is a world where wind speeds reach thousands of kilometers per hour, where the equatorial atmosphere can race ahead of the planet's rotation, and where the boundary between day and night is not a quiet twilight ring, but a zone of rapid flow and sharp gradients. The evidence indicates that, among the known exoplanets, hot Jupiters host some of the most extreme atmospheric circulation patterns ever measured, and these patterns form the backbone of their strange storms. As the winds of a hot Jupiter circle its globe, the air is often hot enough that the ordinary idea of a cloud, made of water droplets or ice crystals, no longer applies. At temperatures of many hundreds to more than 1,000 degrees Celsius, water is a vapor and remains so across wide pressure ranges. Instead, other materials reach their condensation points. Minerals that would be rocks on Earth can become gases and then condense again as tiny solid grains when air cools. In this regime, Storm clouds can be made of silicates, substances built from silicon and oxygen, and related mineral compounds that form the backbone of terrestrial rocks. The storm becomes a cycle of vaporized stone, drifting grains, and precipitation that is more like sand falling from the sky than rain. The first step is a temperature gradient. On a tidally locked hot Jupiter, the day side is heated intensely. The night side cools, sometimes by several hundred degrees Celsius relative to the day side. As air moves from day to night in the upper atmosphere, it can cross a threshold where certain gases become supersaturated, meaning the gas contains more of a substance than it can hold in equilibrium at that temperature and pressure. When supersaturation occurs, condensation can begin. Condensation requires nucleation, the process by which a new phase forms. In Earth's atmosphere, water condenses on aerosols such as dust or sea salt. In a hot Jupiter's mineral clouds, nucleation can occur on microscopic particles, perhaps created by photochemistry or by previous cycles of condensation. It remains uncertain what the dominant nucleation seeds are in many exoplanet atmospheres, because the microphysics cannot be observed directly. Yet models and laboratory studies support that. Once nucleation begins, grains can grow by accretion as molecules stick to their surfaces. Silicate condensation is not a single material. Depending on composition and temperature, different minerals can form. Magnesium silicates such as enstatite and forsterite are often discussed because they are common in cosmic solids and have condensation temperatures relevant to hot Jupiter atmospheres. Other compounds, including aluminum-bearing minerals, can condense at higher temperatures. As the air cools, the sequence of condensation can produce layered cloud decks, with the most refractory, high-temperature condensates forming deeper or nearer to the hottest regions, and lower-temperature condensates forming higher or farther into the night side. The result can be vertical and horizontal structure that changes with circulation. A storm is then not only a moving front, but a shifting boundary between gaseous and solid phases of materials that would be stone in a cooler environment. Observational evidence for such clouds is indirect but accumulating. Many hot Jupiters show muted molecular features in transmission spectra, consistent with high-altitude aerosols. Some show high reflectivity in visible light, suggesting bright clouds that scatter starlight. The color dependence of scattering can hint at particle sizes. Small particles scatter more strongly at shorter wavelengths, producing a slope in the spectrum. Larger particles scatter more evenly, flattening the slope. In some planets, the observed slopes and muted features match expectations for high-altitude haze or cloud particles. Distinguishing a silicate cloud from a hydrocarbon haze is difficult, because both can obscure deeper layers. However, temperature constraints and comparisons across many planets suggest that mineral clouds are plausible in the hotter subset, while photochemical hazes may dominate cooler or differently irradiated atmospheres. The cloud deck is not necessarily global. On the hottest day side, some condensates cannot survive. If temperatures exceed their condensation points, grains evaporate, returning to gas. This creates a powerful asymmetry. Clouds can form where air cools, often toward the night side or on the morning limb, and disappear where air heats, often toward the day side or the evening limb. This pattern can affect phase curves and eclipse measurements. A cloudier morning side can reflect more starlight and alter the visible phase curve, while a clearer evening side can emit more infrared from deeper, hotter layers. Such asymmetries can also change the apparent timing and shape of brightness maxima, complicating the interpretation of winds. In this setting, the storm includes the migration of cloud boundaries as winds carry air across temperature gradients and as particles form and evaporate. Grain growth and settling create another dimension. Once grains form, they can grow to sizes that allow them to fall under gravity. The settling speed depends on grain size, atmospheric density, and gravity. In a low-density upper atmosphere, small grains can remain suspended for long times, carried by winds. Larger grains fall more quickly, potentially clearing the upper atmosphere and depositing material into deeper layers. This settling is a form of precipitation. It is often described as rain, but in many cases it would be a drizzle of solid particles, perhaps with melting or partial evaporation as grains pass into warmer layers. The idea of rock rain is a way to capture the strangeness, but physically it is a sedimentation process. Solids condense, grow, and fall until they evaporate or accumulate in deeper regions. The energy consequences are significant. Clouds and hazes affect how a planet absorbs and emits radiation. A reflective cloud deck can reduce dayside heating by reflecting starlight, cooling the atmosphere below. In infrared, clouds can trap heat by absorbing outgoing radiation, warming layers beneath while cooling layers above. The net effect depends on particle properties and altitude. Because clouds can form and dissipate as air moves, they can create feedbacks with circulation. A cooler region may become cloudier, increasing reflectivity and reinforcing cooling. A warmer region may remain clearer, absorbing more energy and reinforcing warmth. Such feedbacks can sharpen contrasts and influence wind patterns. Observations across multiple hot Jupiters show a diversity of day-night contrasts and reflectivities, consistent with differing cloud regimes. Mineral clouds may also carry electrical consequences. When particles collide and rub, they can exchange charge. On Earth, such charging occurs in volcanic plumes and dust storms as well as in water ice clouds. In an atmosphere filled with mineral grains, charging could occur as particles move in turbulent flows and as they settle through different layers. This raises the possibility of lightning-like discharges, though direct evidence on exoplanets remains uncertain. The upper atmosphere can be partially ionized, and the combination of ions and grains could influence electrical behavior. Still, without direct detections, this remains a plausible mechanism rather than a confirmed feature. The microphysics of condensation is one of the largest uncertainties. The exact particle sizes, shapes, and compositions are not measured directly. Models must assume distributions and compute their effect on spectra. Degeneracies arise because different combinations of particle size and altitude can produce similar spectral flattening. As a result, statements about specific minerals are often tentative. Observations indicate clouds and aerosols. The plausible candidates are guided by temperature and chemistry. The concept of silicate clouds is grounded in known condensation sequences from protoplanetary disks and brown dwarf atmospheres, where mineral clouds are believed to form and have been modelled extensively. In brown dwarfs, rotational brightness variations have been linked to patchy clouds, supporting the idea that mineral cloud decks can be structured and dynamic in warm, high-gravity atmospheres. On a hot Jupiter, the storm becomes a planet-scale weather system that includes a rock cycle in the air. Vapors of silicon and magnesium can exist in the hottest regions. As winds move that air into cooler zones, grains nucleate and grow. Those grains drift with the flow, scatter light, and eventually fall. As they descend, they can evaporate, returning to vapor and ready to be carried again. The cycle does not require a surface. It is an atmospheric circulation loop. It is strange not because it violates physics, but because it uses familiar phase changes on unfamiliar materials. In this region, the strangest exoplanet storms take on texture. They are not only winds measured by heat maps, They are clouds made from the ingredients of rock, forming where air cools and vanishing where it heats. They are precipitation made of mineral grains that fall through hot air and may not survive the journey intact. The evidence for them is written in muted spectra, in reflectivity, and in the shifting patterns of brightness that suggest patchy, changing cloud cover. What is known is that some exoplanet atmospheres are cool enough in parts to let stone condense, and warm enough elsewhere to vaporize it again. The storms are the moving boundary between those states. Beyond silicates, some hot exoplanet atmospheres reach conditions where metals themselves enter the weather cycle. At sufficiently high temperatures, iron and other metals can exist as gases in the upper atmosphere. When air moves into cooler regions, these vapors can condense into clouds and then fall as precipitation. The idea of metal rain is not a metaphor for acid or pollution. It is a direct implication of phase changes under extreme heat. In this region of the topic, the storms are driven by a nightside cold trap that turns a glowing, metal-rich dayside atmosphere into a place where droplets or grains of metal can form and descend. Iron is a central example because its condensation temperature lies within the range expected for some hot Jupiters and ultra-hot Jupiters in their cooler regions. On the day side of the hottest planets, temperatures can rise high enough that many compounds dissociate and atoms exist in simpler forms. Iron can be present as atoms in gas. As winds carry this gas toward the limb and into the night side, temperatures can fall below the condensation threshold for iron. The atmosphere becomes supersaturated with respect to iron, and condensation can begin. Depending on local conditions, iron may condense as liquid droplets or as solid grains. The distinction depends on temperature and pressure. At certain levels, iron could condense as liquid, producing true metallic rain. At other levels, it may solidify quickly, producing a fall of iron grains. Observations cannot yet resolve whether precipitation is liquid or solid in a given planet, but the physical pathways are well constrained by thermodynamics. The mechanism that makes this storm strange is its asymmetry. A tidally locked planet can maintain a permanent hot reservoir on its dayside. Metals evaporate there and remain in vapor form. The night side acts as a sink. Once iron condenses and falls, it can deplete the upper atmosphere of iron-bearing vapor. The circulation then determines whether iron is replenished in the observable layers or trapped below. If the falling iron reaches deeper, hotter layers where it evaporates again, it can be carried upward by mixing and return to the cycle. If it falls into regions where upward mixing is weak, the upper atmosphere could become metal poor on the night side and perhaps even globally. This process is sometimes described as rainout, the removal of condensable species from higher layers. Rainout affects observed spectra by changing which atoms and molecules remain aloft. High-resolution observations offer partial support for this picture. In several ultra-hot Jupiters, atomic metals have been detected in transmission spectra, including iron, magnesium, sodium, and others. These detections indicate that the dayside or terminator regions can contain metals in gas form at high altitudes. In some cases, metal lines appear strong on the evening limb but weaker on the morning limb, or vice versa, suggesting asymmetries in composition consistent with condensation on one side and evaporation on the other. Such interpretations remain challenging because the geometry of a transit samples a ring around the planet, and because winds can shift where particular signatures are strongest. Still, the presence of metal atoms in the upper atmosphere confirms that at least part of the weather cycle involves gaseous metals, a condition very different from solar system planets. Metal condensation influences energy transport. Metals can be strong absorbers of starlight at certain wavelengths. If metal atoms are present high in the atmosphere on the day side, they can absorb stellar radiation and heat those layers, potentially creating or strengthening a temperature inversion. A temperature inversion changes the vertical gradient of temperature and can affect how efficiently the planet radiates energy. It also changes where different spectral lines form. When metals condense out on the cooler side, the absorption decreases and heating shifts. In that way, the chemistry and the thermal structure are linked. The storm is not only winds and precipitation, but also a moving pattern of opacity, a changing filter that determines where starlight deposits energy. The circulation pattern that carries metals across the planet can be fast and turbulent. Day-to-night winds can loft material and mix layers. Yet metal condensation can occur quickly when air crosses the threshold. This creates sharp transitions. Along the terminator where temperatures fall steeply with longitude, a narrow zone may exist where iron begins to condense. In that zone, clouds can form rapidly, changing the local radiative balance. Cloud formation can cool the air by blocking radiation from below, while latent heat released during condensation can locally warm the air. For iron, latent heat per unit mass is substantial, but whether it meaningfully alters circulation depends on the amount condensing and on the surrounding energy budget dominated by stellar irradiation. In many models, radiative forcing remains dominant, but condensation can still shape small-scale structure and variability. The physical form of iron clouds matters. Liquid droplets scatter and absorb light differently than solid grains. Their shapes and sizes influence how they interact with radiation. In a hot, low-density atmosphere, droplets may evaporate or freeze as they fall. The precipitation may not reach a stable surface. Instead, it can fall into warmer layers and re-evaporate, producing a vertical cycle that is largely hidden from direct observation. The visible consequence is the depletion or enhancement of metal lines at certain altitudes, and the presence of cloud opacity in the continuum. Other metals and compounds can join this cycle. Titanium and vanadium, for example, have been discussed because certain oxides can absorb strongly invisible wavelengths and contribute to temperature inversions. However, these species may condense out depending on the planet's temperature profile, removing them from the upper atmosphere. Aluminum-bearing compounds can condense at higher temperatures than silicates and may form deep cloud layers. Calcium and other refractory elements can appear as atoms in ultra-hot conditions. The broader principle is that, in extremely hot atmospheres, the periodic table becomes meteorology. Elements that are solid in ordinary experience can become atmospheric gases and then return to condensed forms in cooler regions. The night-side cold trap can make these storms persistent. Once condensation removes metals from the upper atmosphere on the night side becomes more transparent at some wavelengths, allowing it to cool even more efficiently. This can reinforce condensation. Meanwhile, the dayside remains hot and metal-rich, maintaining strong absorption and heating. The contrast can sustain strong winds. In this way, metal storms are not isolated events. They're a steady regime supported by permanent day-night forcing and by the tendency of condensable metals to migrate toward colder regions. Observationally, there are limits. Detecting metals requires high-resolution spectra and careful separation from stellar lines. Signals can vary with instrument, data processing, and stellar activity. Some claimed asymmetries or variability remain debated. The uncertainty is stated as part of the science observations indicate that metals exist in the upper atmospheres of some ultra-hot Jupiters, and that their distribution may be uneven. it remains uncertain exactly how cloud condensation and rainout proceed in each case, and whether the dominant condensates are iron, silicates, or more complex compounds. Yet the overall framework is robust. In a hot atmosphere, metals can vaporize. In cooler regions, they can condense and fall. Winds connect those regions, and the result is a storm cycle built from metallic phases. Within this region, the stranger storms take on a heavier character. They are not only rock grains drifting through air, they are metallic vapors condensing into droplets or grains, then falling through layers where they may re-evaporate. They are day-to-night transport that carries a metal-laden atmosphere into darkness, where the cold trap removes it from view. The evidence comes through spectral fingerprints of iron and other atoms, through hints of asymmetry between limbs, and through the understanding that a tidally locked hot planet offers a permanent laboratory for extreme condensation cycles. The storm is a global conveyor, and its rain can be made of metal. Some of the best analogues for exoplanet storms are not planets orbiting stars, but objects that sit between stars and planets, glowing faintly on their own. Brown dwarfs are bodies too small to sustain long-term hydrogen fusion, yet massive enough to have deep atmospheres where temperature and pressure create rich cloud layers. Their atmospheres occupy a range that overlaps with giant exoplanets, especially those that are young and still warm. Because brown dwarfs emit their own light, their brightness can be tracked as they rotate, turning patchy cloud patterns into measurable variations. In this region of the topic, storm evidence becomes more map-like. A storm front is not inferred only from a spectrum averaged over time. It is inferred from changes that repeat with rotation, as if different faces of the object carry different weather. The essential observation is a light curve that rises and falls over hours. If the atmosphere were perfectly uniform around longitude, rotation would not change brightness. Variability indicates that some longitudes are brighter or dimmer than others. In infrared, brightness often traces temperature at the layer from which the light escapes, and it also traces cloud thickness because clouds can block deeper, warmer layers. A bright region may be a clearing that reveals hotter depths. A dim region may be a thick cloud deck that hides them. In some cases, different wavelengths vary differently, suggesting that different layers have different patterns. This indicates vertical structure, where clouds at one altitude do not perfectly match clouds at another. The cloud chemistry in brown dwarfs depends on temperature. At higher temperatures, silicate and iron clouds are expected, similar to the mineral and metal condensates discussed for hot exoplanets. At cooler temperatures, other condensates become important, and the atmosphere can develop layered structures with different cloud species at different pressures. The class of objects known as L-dwarfs is typically warmer and often modelled with thick mineral clouds. The cooler T-dwarfs show spectral features of methane and often appear to have less visible cloud opacity, suggesting that clouds sink deeper or break up. Observations across this transition show changes in colour and brightness that have been interpreted as cloud thinning, patchiness, or changes in particle properties. Within this framework, rotational variability becomes a window into cloud patchiness and storm dynamics. The timescales and amplitudes of variability vary widely. Some objects show small, steady variations. Others show large swings that suggest high contrast patchiness. In a few cases, variability evolves over days, implying that cloud features change, merge, or dissipate. This resembles weather, where storms evolve rather than remaining fixed. Yet the driving forces differ. There is no external star heating one side permanently. Instead, the energy source is internal heat rising upward. Rotation and convection organize that energy into patterns of ascent and descent. In a convective atmosphere, hot parcels rise, cool, and sink. Where rising dominates, clouds can form if the ascending air cools below condensation thresholds. Where sinking dominates, air warms and dries, producing clearer regions. The balance can create bands, vortices, and patchy mosaics. The interpretation of brown dwarf variability often involves the idea of cloud holes or breaks. A break in a cloud deck can allow light from deeper, hotter layers to escape, increasing brightness at certain wavelengths. As the object rotates, the break comes into view, brightens the light curve, then rotates away. If multiple breaks exist, the light curve can become complex. Over time, the breaks can change as cloud dynamics shift. This provides a natural picture of storminess. Thick cloud regions move and reshape, while clearer windows open and close. Evidence for organized patterns comes from multi-wavelength monitoring. When brightness variations are measured at different wavelengths, the timing can differ. A peak at one wavelength may occur slightly earlier or later than a peak at another, indicating that the features responsible are not aligned vertically. This suggests that cloud layers at different altitudes can have different shapes, or that temperature variations shift with height. Such phase shifts are analogous to a storm tower leaning with wind shear, or to different cloud decks moving at different speeds. The atmosphere is not a single sheet. It is a stack of layers with their own flows. These observations support the idea that mineral and metal cloud decks can be dynamically structured, with vertical mixing, shear, and waves shaping their appearance. The physics behind this structure draws on fluid dynamics. Rapid rotation tends to organize flow into jets and long-lived vortices. Convection provides upward motion that can create cloud formation zones. Radiative cooling at the top of the atmosphere removes energy and can create stable layers above convective zones. The interface between convective and stable layers can host waves that propagate horizontally and vertically, redistributing momentum. In such environment, storms can persist for many rotations, and some features can last for weeks or months. Yet other features can evolve quickly, indicating turbulent mixing and changing condensation. These analogues matter because exoplanets, especially young giant planets seen in direct imaging, share similar temperature regimes. For directly imaged planets, rotational variability has also been observed or sought, and where detected it suggests patchy clouds on planetary mass objects. The planet's own emitted light carries the imprint of its atmospheric structure. The difference from brown dwarfs is often the presence of a star's gravitational and radiative influence. But for wide-orbit planets, the stellar influence can be weak compared to internal heat, making the analogy closer. In that context, the storms inferred from variability can be seen as cousins of the storms expected on hot Jupiters, but driven more by internal heat and less by extreme day-night forcing. It remains uncertain how directly brown dwarf cloud dynamics translate to all exoplanets. Brown dwarfs have higher gravity than many planets and different compositions depending on formation history. Their atmospheres may have different metallicities and different levels of irradiation, yet the fundamental processes, condensation, mixing, and radiative transfer, are shared. Brown dwarfs demonstrate that mineral clouds can be patchy, that atmospheric features can evolve, and that the resulting variability can be strong enough to measure. They also provide a testing ground for models of cloud microphysics, including particle sizes and sedimentation rates, because their spectra and variability constrain these properties more tightly than many exoplanet observations can. In this region, the storm is read as rotation. It is the repeating rise and fall of brightness, as a cloudy hemisphere turns and presents a different face. It is the subtle mismatch of peaks at different wavelengths, implying layers sliding past each other. It is the evolution of the pattern over days, suggesting storms that grow and decay. The evidence indicates that, in warm atmospheres where minerals and metals can condense, clouds do not form a uniform shell. They organize into patches and bands, and they change. The lesson for exoplanets is that strange materials do not produce static skies. They produce dynamic ones, where cloud decks can break, reform, and drift, leaving a measurable imprint in light. As temperatures and stellar radiation fields vary across exoplanets, aerosols take on forms that blur the boundary between cloud and haze. Some particles form by condensation, where a gas becomes a solid or liquid. Others form by photochemistry, where high-energy light breaks molecules and drives them into new combinations that can polymerize into complex solids. Both pathways can produce layers of particles that scatter and absorb starlight, shaping spectra and thermal structure. In this region of the topic, the strange storms are not only about what falls from the sky, they're about what floats, persists, and spreads as dust and haze, changing a planet's appearance and energy balance in ways that can mimic or amplify weather. One class of exotic condensates involves corundum, aluminum oxide. Corundum is the mineral form of aluminum oxide on Earth, known for gemstones such as ruby and sapphire when it contains trace impurities. In hot exoplanet atmospheres, aluminum-bearing compounds can be among the most refractory condensates, meaning they condense at higher temperatures than many silicates. This places them in deeper or hotter cloud layers, potentially forming a base cloud deck on planets where silicates condense higher up or farther toward the night side. If corundum particles form, they can contribute to opacity at certain wavelengths, and can serve as seeds for other condensates to grow upon. Observationally, identifying corundum specifically is difficult, but its expected presence is part of broader condensation sequences used to model hot atmospheres. The storm implication is that cloud decks may begin with the most heat-resistant materials, creating a foundation for layered mineral weather. Beyond condensation, haze formation can dominate in some planets, particularly those with strong ultraviolet irradiation and abundant carbon-bearing molecules. Photochemical hazes can form when ultraviolet light breaks molecules such as methane, producing reactive fragments that recombine into more complex hydrocarbons. Over time, these can form solid particles, sometimes compared to soot. In the solar system, Titan's orange haze is produced by photochemistry, demonstrating how sunlight can build aerosols in a cold atmosphere. On exoplanets, similar processes can operate under different temperatures and compositions. Hazes can form high in the atmosphere, where ultraviolet light is absorbed and then diffuse or be transported by winds. These hazes can be global, wrapping the planet, or patchy, depending on circulation and production rates. Hazes are especially important because they can flatten transmission spectra. When a haze layer is high and optically thick, it can block light from reaching deeper levels where molecular absorption occurs. This produces a spectrum that appears featureless, with only a weak slope from scattering. Many sub-Neptunes and warm Neptunes show this behavior. The presence of a haze does not necessarily imply a storm in the sense of rapid change, but it can participate in storm dynamics if haze production is localized and then transported. For example, if production is strongest on the day side where ultraviolet flux is highest, then winds can carry haze to the terminator and night side, creating gradients. If removal occurs through coagulation and settling, then the balance between production and loss can create time variability. It remains uncertain in many cases how quickly haze layers can change, because observations often provide snapshots separated by long intervals. Still, the physical processes allow for variability on timescales of days to weeks, particularly when winds are strong and particle growth is efficient. Dust can also be lofted from deeper layers. In convective atmospheres, updrafts can carry particles upward, replenishing haze layers, if condensation occurs deeper. Convective mixing can bring fresh vapor upward, where it condenses into new particles. This can sustain a high-altitude aerosol layer even when particles settle. The resulting sky can be permanently dusty, but with patchiness driven by the changing strength and location of updrafts. In such cases, the storm is not a single rotating feature but a persistent dynamic equilibrium, where particles are continually created, moved, and lost. Radiative effects of hazes are central. A haze layer that absorbs starlight can heat the atmosphere at high altitudes. This can create or enhance a temperature inversion. A heated upper layer can alter circulation by changing pressure gradients and by affecting where winds accelerate. It can also change chemistry by increasing temperatures in regions where photochemistry occurs, shifting reaction rates. Conversely, a haze that primarily scatters light can increase reflectivity and reduce the energy absorbed below, cooling deeper layers. The net effect depends on particle composition and size. For many exoplanets, it remains uncertain whether aerosols are primarily absorbing or scattering, because both can produce similar spectral flattening in transmission. Thermal emission spectra and phase curves can help constrain this by revealing how heat is distributed, but the interpretation remains model-dependent. In the context of strange storms, hazes can create dramatic optical appearances. A planet with a high haze layer can appear larger in transit because the haze increases the effective radius, at which the atmosphere becomes opaque. This can make the planet seem puffier at certain wavelengths. If haze thickness varies with time, the apparent radius can change slightly from one transit to another. Such changes are difficult to confirm, but they are a possible signature of aerosol variability. In addition, hazes can suppress signatures of water and other molecules, complicating attempts to measure atmospheric composition. This suppression is a kind of observational storm, where the atmosphere's changing aerosols obscure the deeper truth. Corundum and other refractory condensates also interact with photochemical products. Mineral grains can provide surfaces for chemical reactions or for the sticking of organic molecules. In complex atmospheres, multiple aerosol populations can coexist, with mineral clouds deeper and photochemical hazes higher. Vertical mixing can connect them. The storm then involves not only motion, but layering, where the upper haze responds to ultraviolet light and the lower cloud responds to temperature and pressure. Circulation can tilt and deform these layers, creating regions where the haze is thinner and deeper, clouds are glimpsed, and other regions where haze is thick and the sky becomes opaque. There is also an important link to particle size. Small haze particles can remain aloft and create strong scattering slopes. Larger particles can form through coagulation, where collisions cause particles to stick. As particles grow, they settle faster. This can thin the upper haze, allowing molecular features to emerge. The growth rate depends on particle density and collision frequency, both of which depend on atmospheric conditions. Variations in mixing and in ultraviolet production can shift particle sizes over time. This provides another pathway to variability without requiring dramatic changes in global circulation. A small shift in particle size distribution can change observed spectra and brightness, creating the appearance of a changing atmosphere. In this region, the strangest storms are storms of opacity and chemistry. They are skies where aluminum oxide may form a deep base cloud, while higher layers are filled with photochemical haze that can hide the gases beneath. They are atmospheres where starlight does not simply heat the air, but manufactures particles that then reshape the climate. The evidence is written in flattened spectra, in scattering slopes, and in the difficulty of seeing molecular features even when temperatures suggest they should be present. Observations indicate that aerosols are widespread among many exoplanets, especially those smaller than Jupiter. It remains uncertain which exact species dominate in many cases, and how rapidly these aerosol layers change. What is clear is that, on many worlds, the most active weather may not be rain or wind seen directly, but the continual creation and movement of dust and haze that turns an atmosphere into a shifting filter between star and space, moving inward from the hottest giant planets and their mineral skies. There are worlds where temperatures fall into ranges that permit water to act as a condensable substance again. Many of these planets are not Earth-like in mass or structure. They're often sub-Neptunes, planets larger than Earth but smaller than Neptune, with thick atmospheres that may be dominated by hydrogen and helium or by heavier volatile gases. In such atmospheres, water can still be abundant as vapor and can also condense into clouds, but the details depend on pressure, composition, and the depth at which water becomes saturated. In this region of the topic, storms become strange in a different way. They are built from familiar molecules, yet they occur in atmospheres whose density, chemistry, and vertical layering can be unlike anything on Earth. Water clouds form when air containing water vapor cools to the point that it can no longer hold all the vapor. On Earth, this often happens as air rises, expands, and cools. The same principle applies on other planets, but the pressure and composition of the surrounding atmosphere change the thresholds. In a hydrogen-rich atmosphere, water can be a minor component by number, but still form clouds because hydrogen does not condense under these conditions. The water saturation curve, the relation between temperature and the vapor pressure at which water condenses, sets where clouds can form. On a sub-Neptune with a warm upper atmosphere and high pressures below, the level where water becomes saturated may be deep, at pressures far higher than those probed by typical transmission spectra. This creates a challenge. The planet may have water clouds, but they may be hidden beneath hazes or above layers that are too deep to observe directly. Observations indicate that many sub-Neptunes show muted or flat transmission spectra, suggesting high-altitude aerosols. This can mask deeper cloud layers and make it difficult to detect water vapor features. When features are detected, they can be small, implying either a low abundance of water in the observable atmosphere, high-altitude clouds that truncate the path, or a high mean molecular weight atmosphere that reduces scale height. Each interpretation leads to different expectations for storms. A high mean molecular weight atmosphere, perhaps rich in water vapor, carbon dioxide, or nitrogen, would be denser and could support different circulation patterns. A hydrogen-rich atmosphere would be more extended and could transport heat differently. In many cases, it remains uncertain which regime applies because the same observed spectrum can be explained by multiple combinations of composition and clouds. In a tidally locked sub-Neptune, day-to-night circulation can create strong gradients. If water vapor is abundant, it can condense preferentially on the cooler side or at higher latitudes where temperatures are lower. This can create persistent cloud decks in certain regions. If clouds are bright, they can reflect starlight, cooling the day side beneath them and potentially shifting circulation. If clouds are thick in infrared, they can trap heat and warm deeper layers. The storm, then, may not be a discrete thunderhead but a broad, shifting region of cloud formation along temperature contours, shaped by circulation and by the planet's permanent day-night pattern. Water condensation also involves latent heat, the heat released when vapor becomes liquid or ice. On Earth, latent heat is central to powering convection and storms. In thick exoplanet atmospheres, latent heat can also influence dynamics, but its importance depends on the fraction of condensing vapor and on the background energy flow. In a hydrogen-rich atmosphere, water may condense but represent a small mass fraction, limiting the energy release. In a water-rich atmosphere, condensation could involve large amounts of mass and thus large energy release, potentially powering strong convection. It remains uncertain how common truly water-dominated atmospheres are among sub-Neptunes, because atmospheric escape and formation histories can produce a wide variety of outcomes. Observations and models suggest that some sub-Neptunes could have significant water content, but the exact distributions are debated. The vertical structure of these atmospheres can include multiple cloud layers. At higher altitudes, photochemical hazes can form, creating a persistent veil. Beneath that, water clouds may form where temperatures and pressures cross saturation. Deeper still, other volatiles such as ammonia can condense on cooler planets, though ammonia condensation typically requires lower temperatures than water. The presence of multiple layers means storms can be hidden from view. A planet may have active convection and cloud formation, yet the upper haze layer makes the spectrum appear calm and featureless. The storm energy may be trapped below, expressed indirectly through heat transport and perhaps through variability in the thickness of the upper aerosols. Phase curves provide some access. For a planet that emits measurable infrared light, a phase curve can reveal whether the day side is much warmer than the night side. If the contrast is small, winds are transporting heat efficiently. If the contrast is large, transport is less efficient or radiation is fast. Clouds can influence this by altering where the emission emerges. If the dayside has thick clouds that block deep emission, the observed dayside temperature can appear cooler even if deeper layers are hot. If the night side has clouds that trap heat, it can appear warmer. Thus, cloud distribution can masquerade as a change in wind efficiency. In a stormy atmosphere, the cloud map itself can be dynamic, leading to changes in phase curves over time. The term storm, in this context, can also include global-scale cloud belts and wave patterns. In a rapidly rotating planet, the Coriolis effect can organize flow into jets, producing banded structures similar in concept to Jupiter's belts and zones. In a tidally locked planet, the dominant pattern can be a day-to-night flow with jets embedded. Waves can propagate and create alternating regions of convergence and divergence, where clouds form and dissipate. The resulting pattern could be patchy and mobile. If the planet is observed over many orbits, slight changes in brightness or spectral slope could indicate shifting cloud cover. Detecting such variability is difficult for small planets because their signals are faint, but it is a goal of repeated observations. Water clouds in these atmospheres may not behave like Earth's water clouds in texture or droplet size. The surrounding gas is different, pressures can be higher, and gravity may differ. Droplet growth depends on condensation rates and on collision processes. If updrafts are strong, droplets can be lofted and grow. If updrafts are weak, droplets may form thin layers and settle. At very high pressures, supercritical behavior can occur in deeper layers, where the distinction between liquid and gas becomes less meaningful. This is likely below observable levels for most planets, but it shapes the deep climate and the reservoir of water vapor available above. Uncertainty is central. Observations indicate that many sub-Neptunes are cloudy or hazy. Some show hints of water vapor or other molecules, but the signals are often small. It remains uncertain where water clouds sit in the vertical profile and whether they are thick and active or thin and stable. Yet physics suggests that, in planets with suitable temperatures, water will condense somewhere. When it does, it will change the radiative balance and participate in circulation. The strangeness comes from context. Familiar water clouds may exist beneath skies of haze, in atmospheres thick with hydrogen, on worlds where the surface may be thousands of kilometers below the cloud tops, or may not exist as a solid boundary at all. In such settings, storms can be present yet hidden, shaping the planet's heat and light in ways that only careful observation can infer. Farther into cooler regimes, the dominant condensable substances can shift from water to hydrocarbons and other volatiles. On cold giant planets, and on some colder exoplanets, methane becomes a key player. Methane is stable at low temperatures, and it can exist as a gas that condenses into clouds when air cools sufficiently. In the solar system, methane clouds are part of the weather on Uranus and Neptune, where storms can appear as bright cloud outbreaks. For exoplanets, methane is also a prominent molecule in spectra when temperatures permit it, and its presence signals a chemical environment where carbon is carried in a reduced form rather than primarily as carbon monoxide. In this region of the topic, storms become cycles of methane condensation and evaporation, shaped by weak starlight, long radiative timescales, and the internal heat of the planet. Methane condensation is governed by saturation, as with water, but it occurs at lower temperatures. In a hydrogen-rich atmosphere, methane can be a trace gas by number yet still form clouds if temperatures cross the threshold. The vertical level of methane clouds depends on temperature profile and pressure. On cold giants, cloud layers can be stacked, with deeper water clouds, intermediate ammonia clouds, and higher methane clouds, though the exact ordering depends on temperature and composition. For exoplanets, methane clouds are most plausible on planets with equilibrium temperatures low enough for methane to be stable and to condense, but still warm enough that the atmosphere is active and not frozen into quiescence. The energy budget in these worlds differs from hot Jupiter's. Starlight is weaker, and in many cases internal heat becomes comparable to or larger than absorbed stellar energy. Internal heat rises from deep layers and can drive convection. Convection carries methane-rich air upward. As it rises, it cools and can reach methane saturation. Clouds then form, and methane can condense into droplets or ice particles depending on local temperatures and pressures. This condensation releases latent heat, which can strengthen the buoyancy of rising parcels and power further ascent. In this way, methane storms can become convective outbreaks, with cloud towers that rise and spread. The scale of these features depends on gravity, rotation, and the background stability of the atmosphere. Rotation organizes the flow into jets, as on solar system giants. Jets can create bands of rising and sinking motion. Where air rises, clouds form. Where air sinks, clouds evaporate. This produces belts and zones with different cloudiness. On Neptune, for example, bright methane clouds can appear near regions of upwelling and shear. For exoplanets, direct imaging or phase curve monitoring might reveal such patterns if the planets are bright enough. However, most cold exoplanets are difficult to observe in detail because their orbital periods are long and their thermal emission is faint. The analogy is nonetheless useful because it anchors methane storms in known physics of hydrogen-rich atmospheres. Methane can also participate in photochemistry. Ultraviolet light can break methane and lead to the formation of more complex hydrocarbons that can create haze particles. On Titan, methane photochemistry produces a thick, orange haze on a cold giant planet closer to its star. Photochemical hazes could form and coexist with methane clouds. The haze can absorb sunlight and heat upper layers, potentially creating temperature inversions and affecting where methane condenses. It can also obscure deeper clouds, flattening spectral features. Thus, methane storms may be accompanied by hazes that both arise from methane and modify methane's own cloud cycle. Seasonal forcing can matter in these colder systems. If a planet has an axial tilt and a long orbit, different hemispheres may receive different solar input over time. Seasonal changes can shift the altitude and latitude where methane clouds form. They can also change the strength of jets and storm tracks. For a tidally locked cold planet around a small star, the day-night contrast may still dominate. For a planet with a longer period and faster rotation not locked, seasonal cycles could produce moving zones of condensation. In both cases, storms become tied to slow changes in insolation rather than to rapid diurnal cycles. Observations of methane in exoplanet atmospheres provide constraints on temperature and chemistry. Methane features in near-infrared spectra have been sought, and in some cases detected, especially in directly imaged young giant planets and brown dwarfs. The presence of methane is sometimes weaker than expected, suggesting disequilibrium chemistry, where vertical mixing brings carbon monoxide-rich gas upward faster than it can convert to methane. This indicates active mixing, which is itself a sign of dynamic weather. In that context, methane storms are not only about condensation, but about the competition between chemistry and transport. Where methane is suppressed, clouds may be different, and the haze production pathways may change. At low temperatures, cloud particles can be solid, and their scattering properties differ from liquid droplets. Methane ice particles can reflect sunlight strongly, and also scatter thermal emission. Their sizes and shapes influence brightness and spectral slopes. If storms loft particles high, they can create bright features against darker backgrounds. As seen in some solar system planets, on exoplanets, such brightening could produce rotational variability. The challenge is that such signals are small and require long monitoring, yet the principle remains patchy. Methane clouds can create brightness variations as the planet rotates. Methane cycles can also involve precipitation that reaches deeper layers. Falling methane ice can sublimate or melt if it enters warmer regions, returning to vapor. This forms a vertical cycle similar in concept to the rock and metal rain cycles of hotter planets, but with a familiar volatile. The strangeness lies in scale and context. A methane storm could occur in an atmosphere where the ground is not a solid surface, but a deep, high-pressure fluid layer. It could be driven by internal heat rather than sunlight. It could be modulated by long seasons or by strong jets that wrap the planet. The limits of knowledge are again central. For most cold exoplanets, storms are not directly observed. Methane itself can be hard to detect because clouds and hazes can mute spectral features, and because temperatures and metallicities can shift chemical balances. Observations indicate methane in some directly imaged objects and suggest mixing-driven disequilibrium in others. It remains uncertain how common methane cloud storms are among the broader exoplanet population, especially among older, colder planets that are faint. Yet based on atmospheric physics and on solar system examples, methane condensation should occur when temperatures allow it and when methane is present. When it does, it can produce clouds, release latent heat, and support convective bursts and banded weather patterns. In this region, The strangest storms are quieter in radiative intensity but rich in chemistry. They are storms where carbon in methane moves between gas and ice, where ultraviolet light can turn methane into haze, and where internal heat can drive upward plumes that build clouds in cold skies. They represent a shift from minerals and metals to volatiles, yet the underlying structure remains temperature gradients, circulation, condensation, and the continual exchange between what is airborne and what falls. Between the very hot giants and the colder methane-dominated worlds lies a wide population of intermediate planets, often called mini-Neptunes and warm Neptunes. These planets have radii and masses that place them between Earth and Neptune, and they likely possess substantial atmospheres. Their temperatures can range from a few hundred degrees Celsius down to near the limits where water and other volatiles can condense. Because their atmospheres can be thick but not necessarily dominated by hydrogen alone. Their circulation and storms can differ from both hot Jupiters and colder giants. In this region of the topic, the strange storms arise from the way planet size, gravity, and atmospheric composition reshape wind patterns and cloud behavior. A key distinction is scale height. In a hydrogen-rich atmosphere, the mean molecular weight is low, and the atmosphere is more extended for a given temperature and gravity. In a heavier atmosphere, rich in molecules such as water vapor, carbon dioxide, nitrogen, or other volatiles, the mean molecular weight is higher, and the atmosphere is more compact. This changes both the observational signature and the dynamics. A compact atmosphere can have sharper vertical gradients and shorter distances over which pressure changes. An extended atmosphere can have broad, diffuse layers where clouds and hazes spread. The same level of stellar heating can produce different wind speeds and wave patterns depending on density and thickness. Mini-Neptunes also occupy a regime where atmospheric escape can reshape composition over time. Some may begin with hydrogen-rich envelopes and lose part of them under stellar irradiation, leaving behind heavier atmospheres. This creates diversity. Two planets of similar size and temperature can have different gas mixtures and thus different weather. In a hydrogen-rich mini-Neptune, circulation may resemble that of a scaled-down hot Jupiter, with strong day-to-night winds if tidally locked, and with equatorial jets influenced by rotation. In a heavier atmosphere, heat capacity and radiative properties differ, and winds may respond differently to the same forcing. The storm regimes can therefore vary widely even within the same broad category. The role of superrotation, an eastward equatorial jet, can persist in these planets, especially if they are tidally locked and strongly irradiated. Models suggest that day-night heating patterns generate large-scale waves that converge momentum toward the equator, producing an eastward jet. The strength of this jet depends on radiative timescales and on frictional or drag processes, including possible magnetic drag if the upper atmosphere is sufficiently ionized. In a warm Neptune, temperatures may be lower than in ultra-hot Jupiters, reducing ionization and magnetic effects. This can allow jets to remain strong. At the same time, clouds and hazes can alter radiative timescales, changing how quickly the atmosphere cools as it moves into night. If cooling is slow, heat is transported efficiently and contrasts are reduced. If cooling is fast, contrasts sharpen and winds can intensify near the terminator. Cloud composition shifts with temperature. In some warm Neptunes, clouds may include sulfide and salt condensates, such as sodium sulfide and potassium chloride, substances that can condense at temperatures where silicates remain vapor, but water may still be gas. These clouds are exotic in composition, yet less extreme than rock and metal rain. They can form high in the atmosphere and can produce strong opacity in visible and infrared wavelengths, flattening spectra. Their distribution can be patchy if condensation occurs preferentially on the cooler side or at higher latitudes. As winds move air through different thermal regimes, these clouds can form and evaporate, creating dynamic fronts. Evidence for such condensates is indirect and often framed as plausible candidates rather than confirmed species. Observations indicate that many warm Neptunes and mini-Neptunes have high-altitude clouds and hazes. Some show scattering slopes and muted molecular features. In a few cases, specific molecules such as water vapor or methane have been detected, but cloud opacity often dominates. This uncertainty means the storm description must remain grounded in what can be inferred there are aerosols. They likely vary with temperature, and they influence energy transport and observed spectra. The intermediate size of these planets also affects Rossby deformation scale, a measure of how large weather systems can become before rotation constrains them. On larger planets, rotation can organize flows into multiple jets. On smaller planets, circulation patterns can be simpler or dominated by fewer broad jets. Mini-Neptunes sit between these extremes. Depending on rotation rate and atmospheric thickness, they may support one dominant equatorial jet and weaker high-latitude jets, or they may develop more complex banding. The resulting storms could be broad, spanning much of a hemisphere, or organized into bands and vortices. The exact pattern depends on parameters that are often uncertain, such as rotation period and drag. The vertical structure of these atmospheres can include a strong stratified layer above and deeper convective regions below. In deeper layers, internal heat may contribute, especially if the planet retains formation heat. Convection can transport heat upward and can produce waves that influence upper-level winds. Cloud formation may occur near the boundary between convective and stable layers, where rising air cools enough for condensation. If this boundary shifts with time or varies with latitude, cloud belts can migrate. Such migration could create long-term variability in observed properties. There is also the possibility of ocean-like layers beneath atmospheres in some intermediate planets, not as liquid water oceans necessarily, but as deep layers of supercritical fluids where distinction between gas and liquid is blurred. Such layers would be at pressures far beyond observational reach, yet they can influence how heat is stored and released. A planet with a deep, volatile, rich interior may have a different internal heat flux than one with a more rock-dominated structure. Over time, internal heat can influence atmospheric stability and thus storm activity. The observational signatures of storms on mini-Neptunes are often subtle. Phase curves can reveal heat redistribution. Transit spectra can reveal changing haze thickness or cloud top pressure. Repeated observations might show variability in transit depth at certain wavelengths, suggesting changing aerosol layers. Detecting such variability requires precision and careful control of stellar activity effects. Where it is tentatively reported, it points to atmospheres that are not uniform and may change over timescales of months to years. It remains uncertain whether such changes reflect weather, seasonal cycles, or longer-term evolution of aerosol production. In this region, the strangest storms are shaped by ambiguity and diversity. These worlds can host clouds made of salts and sulfides, hazes produced by photochemistry, and water clouds deeper down. Their winds can form equatorial jets that shift hotspots, while their composition can change the very thickness and responsiveness of the air. The same planet category can include both extended hydrogen-rich atmospheres and compact heavier ones, leading to fundamentally different storm behaviors. What is known is that mini-Neptunes are common in the galaxy, and many appear cloudy. The physics implies that, where temperature gradients and condensation thresholds intersect, clouds will form and winds will move them. The storms of these intermediate worlds are therefore not defined by a single exotic ingredient, but by the way size and composition combine to create weather regimes that sit between the extremes of rock rain and methane snow. Electrical storms are among the most familiar dramatic events in planetary weather, yet they are also among the hardest to confirm on exoplanets. Lightning is a rapid electrical discharge through an atmosphere, produced when charge separation becomes strong enough to break down the insulating properties of air. On Earth, charge separation is tied to collisions between ice particles and graupel in convective clouds, aided by updrafts. In volcanic plumes and dust storms, charge separation can also occur through frictional contact between particles. On exoplanets, both cloud microphysics and atmospheric composition can be very different. Yet the underlying requirement remains the same: a mechanism that separates charge and a medium that can hold that separation until breakdown occurs. In this region of the topic, storms turn inward toward chemistry, ionization, and the possibility of lightning-like processes in atmospheres made of unfamiliar materials. Charge separation on exoplanets could arise from several pathways. In mineral and metal cloud decks, collisions between solid grains could transfer electrons, much as in terrestrial dust storms. In water or methane cloud systems, collisions between liquid droplets, ice particles, and mixed-phase aggregates could produce charging in ways closer to Earth's. The efficiency of charging depends on particle composition, size distribution, and turbulence. It also depends on the presence of updrafts strong enough to keep particles suspended and colliding. On some hot planets, convection in the upper atmosphere may be weak because stronger radiation creates stable layers, yet deeper convection may still occur. And cloud layers on the night side or at certain latitudes could have more vigorous vertical motion. On cooler planets, convection may be more active, providing a more direct pathway to charge separation. The presence of ions affects electrical behavior. In upper atmospheres heated by ultraviolet radiation, ionization can increase conductivity, allowing charge to leak away and making lightning harder to sustain. In lower, denser layers, conductivity can be lower, allowing charge to build. This suggests that lightning may be more likely in deeper cloud layers rather than in the highly ionized upper atmosphere. On hot Jupiters, the upper atmosphere can be partially ionized, while cloud formation may occur lower or on cooler regions. This separation could create zones where charging occurs in a relatively insulating environment and where discharges can propagate through surrounding gas. The details remain uncertain because ionization profiles and cloud locations are not well constrained observationally. Evidence for lightning on exoplanets has been sought through radio emissions and through optical or infrared signatures. Lightning produces broadband radio bursts and also emits light across many wavelengths. However, at interstellar distances, such signals are faint. Radio searches have often been limited by sensitivity and by confusion with stellar radioactivity. Optical flashes would be overwhelmed by starlight for most systems. Another proposed signature is chemical. Lightning can drive high-temperature reactions along the discharge path, producing transient molecules such as nitrogen oxides in nitrogen-rich atmospheres or altering the balance of carbon and hydrogen species. In a hydrogen-rich atmosphere, lightning could produce molecules that would otherwise be rare, such as hydrogen cyanide, acetylene, or other complex organics, depending on available carbon and nitrogen. Detecting these products requires high-quality spectra and the ability to distinguish lightning-driven chemistry from photochemistry and equilibrium chemistry. At present, observations indicate complex chemical environments in some exoplanets, but attributing specific molecules to lightning remains uncertain. Even without direct lightning detection, Storms that involve strong charging could influence aerosol properties. Charged particles can stick together differently, affecting coagulation and settling. Electric fields can align particles and influence how clouds grow. In a mineral cloud, charging could lead to enhanced aggregation, creating larger grains that settle faster and thin the cloud deck. In a haze layer, charging could influence how organic particles coagulate. These effects would be indirect and difficult to isolate, but they illustrate that electrical phenomena can feed back on observable weather. Chemical storms also involve ion chemistry at high altitudes. Ultraviolet radiation and energetic particles can create ions that react rapidly. In hydrogen-rich atmospheres, ions such as H3+ can form and participate in chain reactions. In atmospheres with water, carbon monoxide, or methane, ion chemistry can produce complex molecules and can affect haze formation rates. This chemistry is often most active on the day side where ultraviolet flux is greatest, and it can be transported by winds to other regions. Thus, the storm is a moving chemical pattern, where the atmosphere's composition changes with longitude and altitude as it flows between irradiation regimes. One of the most measurable chemical signatures tied to storms is variability in spectral features associated with specific species. If an atmosphere has patchy clouds or temperature variations, the apparent abundance of a molecule can change in the observed spectrum because the viewing geometry samples different pressures. A deeper view reveals more molecular absorption. A cloudier view reveals less. Over time, this can produce apparent abundance changes even if the bulk composition is stable. In repeated observations, such variability could be interpreted as a chemical storm, but it may be a cloud storm masquerading as chemistry. The distinction requires coordinated measurements at multiple wavelengths and careful modeling of cloud effects. Temperature also couples to chemistry through dissociation and recombination. In ultra-hot atmospheres, molecules can break apart on the day side and recombine on the night side. Water can dissociate into hydrogen and oxygen-bearing fragments. Hydrogen can react to form hydroxyl and other radicals. As air moves across the planet, it carries these fragments and allows recombination in cooler regions. This creates compositional gradients that track circulation. Observations indicate that some ultra-hot Jupiters show weaker water features than expected, consistent with dissociation at high temperatures. Night-side recombination may restore water, but whether it is observable depends on cloud cover and emission depth. This is a chemical storm driven by temperature extremes, with the planet's circulation acting as the conveyor for reacting gases. Lightning-like discharges, if present, could interact with this environment by providing localized bursts of high temperature and ionization. Even in the absence of confirmed lightning, the combination of strong winds, particle-laden clouds, and steep temperature gradients suggests that electric fields could arise. In mineral clouds, collisions between grains in turbulent shear zones could produce charging. In water-rich convective storms, updrafts could separate charge in ways more familiar. The level of confidence varies. Observations do not yet provide unambiguous lightning detections on exoplanets. What they do provide is evidence for conditions that could support electrical phenomena, thick clouds, strong winds, and chemical disequilibrium that indicates active mixing and irradiation. Within this region, the strangest storms are storms of reaction and charge. They are atmospheres where molecules are broken by light and rebuilt in darkness, where cloud particles may carry charge as they collide and fall, and where the possibility of lightning remains an open question constrained by physics and limited by measurement. This science proceeds by seeking indirect traces, unusual molecules, unexpected variability, and radio or infrared signals that could, one day, distinguish an electrical storm from a purely meteorological one. What is known is that chemistry and electricity are not separate from weather. They are part of how an atmosphere moves energy and matter, and on exoplanets they may operate under conditions that make even familiar phenomena take unfamiliar forms. Beneath the upper layers shaped by starlight and aerosols, there is a deeper engine that can power storms for a long time internal heat. Giant planets and many sub-Neptunes retain heat from formation and also generate heat through slow contraction and, in some cases, tidal dissipation. This heat rises from the interior towards space. Where it meets layers that can cool efficiently, convection can form, carrying energy upward in plumes. Convection is the buoyant rise of warm, less dense fluid, and the sinking of cooler, denser fluid. In planetary atmospheres, convection can build storm systems by creating concentrated updrafts, generating clouds through cooling of rising air, and feeding turbulence that organizes into vortices. In this region of the topic, storms become less tied to the star and more tied to the planet itself, to a steady inward source of energy that can sustain long-lived features. Internal heat flux varies widely. A very young giant planet can be warm and luminous, radiating strongly in infrared. An older planet can cool and dim, yet still emit more energy than it absorbs from starlight if it is far from its star. Even close-in planets can retain internal heat, though stellar irradiation often dominates their upper atmospheres. The deeper layers, however, can remain influenced by internal convection. This matters because storms often draw from the contrast between deep warmth and upper cooling. If the atmosphere can radiate energy effectively from its top layers, those layers cool, become denser, and sink, while warm material rises to replace them. The result is convective overturning that can create localized storm regions and broad patterns. On the solar system giants, internal heat is associated with belts, zones, and long-lived vortices such as Jupiter's Great Red Spot. While exoplanets cannot yet be imaged with comparable detail, the physics indicates that similar processes could operate in giant exoplanet atmospheres, especially those not dominated by extreme stellar forcing. In warm but not ultra-hot planets, internal heat can interact with starlight, producing a hybrid regime where dayside heating shapes upper winds, while internal convection shapes deeper storm formation. The storms of such planets could have deep roots and shallow expressions, with convection generating waves that influence the observable atmosphere. Deep convection can also interact with cloud formation. If a condensable substance exists in deeper layers, convection can transport it upward. Rising air cools, condenses, and releases latent heat, enhancing buoyancy. This positive feedback can create powerful convective storms. The condensable could be water in warmer giants, ammonia in cooler ones, methane in colder ones, or even mineral vapors in very hot environments at certain depths. The key is that internal heat supplies the background energy and mixing that can deliver condensable materials to cloud-forming regions. A storm becomes a column that links deep reservoirs to upper layers, even if the uppermost layers are partly masked by haze. The depth of convection depends on stability. Some atmospheres develop radiative zones where heat is transported mostly by radiation rather than by convection. In such zones, the temperature gradient is shallow and buoyancy is suppressed. Convection occurs below, where the gradient is steep enough. The boundary between convective and radiative regions can act as a wave generator. Plumes that rise and overshoot can excite waves that travel horizontally. These waves can organize jets and vortices. They can also create periodic patterns of rising and sinking that modulate cloud formation. Thus, even when convection is deep and hidden, it can still influence the observable atmosphere through waves and large-scale circulation. Storm persistence arises when rotation stabilizes vortices. A vortex is a rotating region of fluid. In a rapidly rotating atmosphere, vortices can become long-lived because rotation and stratification limit vertical mixing that would otherwise dissipate them. Vortices can trap aerosols and heat, creating localized brightness features. In brown dwarfs, rotational brightness variations suggest that large-scale features can persist for many rotations, consistent with stable vortices or bands. For exoplanets, especially those that can be monitored in emitted light, similar persistence could produce stable periodic signals. Variability in those signals could indicate evolving storm structures, mergers, or shifts in cloud coverage. Internal heat can also create upward transport of disequilibrium species. In chemical equilibrium, composition at a given pressure and temperature is predictable. Vertical mixing can disrupt this by moving gases faster than they can react. Carbon monoxide and methane balance is one example, as are nitrogen species and sulfur species. When internal convection is strong, it can dredge up gases from deep layers and imprint them in upper atmospheres. Observations of disequilibrium chemistry are therefore indirect evidence of vigorous vertical mixing, which is often associated with convective activity. This mixing can also supply aerosols or cloud seeds, contributing to storm formation and persistence. On some planets, internal heat may be enhanced by tides. A planet in an eccentric orbit can be flexed repeatedly, dissipating energy. This can raise internal temperatures and increase convective vigor. Even if the orbit is nearly circular, interactions with other planets can maintain slight eccentricity over long times. In such cases, storms might be more active than expected from starlight alone. It remains uncertain how often tidal heating significantly boosts internal heat in the observed exoplanet population, because internal heat flux is difficult to measure directly. However, inflated radii and certain thermal emission properties suggest that extra heating exists in some close-in giants, and tides remain one plausible contributor. The expression of deep convection at the top of the atmosphere depends on opacity. If the upper atmosphere is hazy and cloudy, it can hide the temperature contrasts and cloud structures created below. The planet may appear smooth in spectra, even if storms rage beneath. Yet deep convection can still affect global heat redistribution, influencing phase curves and day-night contrasts. It can also influence the depth of the observable photosphere by changing cloud top pressures. Over time, changes in convective vigor could lead to changes in cloud coverage and thus in observed properties. In this region, the strangest storms are not strange because of exotic chemistry alone. They are strange because they can be powered from below for long periods, forming features that may last far longer than terrestrial storms. They are strange because they may be hidden beneath hazes and still shape a planet's emitted light and spectral fingerprints. They are strange because a planet's interior, cooling slowly over billions of years, can sustain weather regimes that are steady yet complex. Observations indicate mixing, variability, and in some cases temperature structures consistent with dynamic atmospheres. It remains uncertain what specific storm morphologies dominate on most exoplanets, because the data are limited. What is grounded is the energy pathway. Internal heat rises, convection forms, waves and vortices organize, and clouds respond. Inward from the starlit layers, the planet's own warmth becomes a deep driver of storminess. As attention moves deeper into an atmosphere, Pressure increases and the behavior of gases and clouds changes. The upper atmosphere is a place where light escapes and where clouds and hazes can sit as thin veils. Deeper down, the air becomes dense, collision rates rise and phase boundaries shift. Condensed particles that float at low pressures can dissolve or evaporate. Chemical reactions that are slow in thin air can proceed rapidly in dense air. The storm, when traced downward, can become hidden behind pressure, transformed from visible cloud fronts into motions and phase changes occurring in layers that cannot be directly observed. In this region of the topic, the strange storms are those sealed beneath, driven by dynamics and chemistry in compressed environments where familiar distinctions, such as clear air versus cloudy air, can blur. The first change with depth is radiative visibility. Observations typically probe pressures from a fraction of a bar to a few bars in many exoplanets, sometimes somewhat deeper depending on wavelength and cloud opacity. Below that, the atmosphere can become opaque due to molecular absorption and due to clouds. The level from which most thermal radiation escapes is called the photosphere, but on a planet it is not a sharp surface. It is a band of depth that depends on wavelength. In a cloudy atmosphere, the photosphere can sit high. In a clearer atmosphere, it can sit deeper. Storms can shift this effective photosphere by moving clouds. Yet below the deepest photospheric layers, storms may continue with little direct imprint on emergent light. Pressure influences condensation in ways that can reverse expectations. At higher pressures, saturation vapor pressures change and condensation thresholds shift. Some species that condense at low pressure can remain gaseous at higher pressure because the temperature rises and because the thermodynamic balance shifts. Conversely, some species can condense deeper where pressure is high and temperatures cross specific curves. The atmosphere can host multiple cloud bases. A cloud deck that is prominent in upper layers can disappear as particles settle and evaporate in warmer depths. While new cloud decks form deeper in a hot Jupiter, mineral clouds may form at certain pressures on the night side and evaporate on the day side. Deeper down, temperatures may be high enough everywhere that those minerals cannot exist as solids, erasing that cloud layer. The storm then becomes an oscillation around a cloud base that exists only within a limited depth range. Particle fate changes under pressure at low density. Particles settle slowly and can remain suspended. At higher density, drag changes, and settling can become faster or slower depending on regime. But collision and growth rates increase. Particles can grow larger through coagulation, making them fall more efficiently. They can also dissolve if they enter layers where they are no longer stable. For example, a silicate grain falling into hotter, denser air can evaporate, returning to vapor. An iron droplet can evaporate or react with surrounding gases. The precipitation cycle can therefore be mostly a cycling between phases within a certain band of pressures, with little net delivery to a deep boundary. Chemistry also changes. In upper atmospheres, photochemistry dominates because ultraviolet light drives reactions. Deeper down, light is weaker and temperature and pressure dominate chemistry. Many reactions approach equilibrium, with compositions set by local conditions. Yet storms, through vertical mixing, can carry gases upward and downward, creating disequilibrium. The deeper layers act as reservoirs, and storms act as pumps. In dense layers, conversion between carbon monoxide and methane can proceed, but the timescale depends strongly on temperature and catalysts. Vertical mixing can pull methane-poor gas upward into regions where methane would otherwise be expected, or it can push methane-rich gas downward where it converts. This continual exchange creates chemical gradients that can persist even when equilibrium is favored locally. In some atmospheres, pressure and temperature can reach conditions where certain fluids become supercritical. A supercritical fluid is a state where the distinction between liquid and gas disappears. Water, for example, has a critical point at high temperature and pressure. Above that point, there is no separate liquid phase. In a deep atmosphere rich in water, there could be regions where water exists as a supercritical fluid mixed with other gases. This can change how heat is transported and how condensation occurs above. Instead of a sharp boundary between a vapor layer and a liquid ocean, there may be a continuous transition. This alters the deep water cycle. A storm above may not draw moisture from a surface ocean. It may draw it from a deep, compressed reservoir where water is neither typical gas nor typical liquid. Similarly, in hydrogen-rich giants, deep layers may involve molecular hydrogen transitioning toward metallic hydrogen under extreme pressure, though that occurs far deeper than any atmospheric storm layers accessible to current observation. Yet even before such extremes, the compressibility and heat capacity of dense hydrogen influence convection. The deeper the atmosphere, the more the adiabat, the temperature profile set by convection, can determine conditions. Storms can be manifestations of deviations from that profile, localized plumes that carry heat upward more efficiently than the background. The dynamics of deep layers can be more sluggish in one sense and more powerful in another. Radiative cooling is weaker because photons cannot escape easily. This can lengthen thermal timescales. Changes can persist longer. At the same time, the density is high, so the momentum of moving air is larger, and convective plumes can transport significant energy. The storms may not flicker. They may pulse on longer intervals, driven by slow accumulation of instability and then rapid release. The evidence for such deep variability is indirect, potentially seen as long-term changes in emitted flux or in cloud coverage at observable levels. A separate pressure effect involves sound speed and wave propagation. In dense air, waves can carry energy and momentum efficiently. Gravity waves generated by convection can travel upward, and as density decreases they grow in amplitude until they break, depositing momentum. This process can drive jets and shape upper wind patterns. Thus, deep storms can shape upper storms without being visible themselves. The deeper region is where waves are born. The upper region is where they break and reshape circulation. The link is continuous, but observation sees mostly the outcome, not the source. The storms sealed beneath pressure also create challenges for interpretation. When a spectrum indicates a certain cloud top pressure, it does not reveal what lies below. A planet could have a thin upper haze above a deep convective cloud layer. Another could have a thick, stable cloud deck above relatively calm deeper layers. Both might look similar at certain wavelengths. Models help, but degeneracies remain. It is therefore important to state what is known. Observations constrain conditions near the photosphere and above. It remains uncertain how deep storm systems extend and how much of the planet's weather energy is processed below observable layers. In this region, the strangest storms are those that are physically real yet observationally hidden. They are phase changes occurring in compressed air, where clouds form and vanish within narrow depth bands. They are vertical pumps that move gases between deep reservoirs and upper layers, maintaining chemical patterns that do not match local equilibrium. They are convective plumes that drive waves, shaping jets far above. They are slow pulses of instability in layers that cool reluctantly. The atmosphere grows thicker, the light grows dimmer, and the storm becomes an inward phenomenon, sense through its influence on what can be seen rather than through direct signatures of its own. At the deepest end of what can be discussed meaningfully as atmospheric storm behavior, models approach layers where pressure is high, temperatures are high, and the distinction between atmosphere and interior becomes gradual. For rocky planets, this would be the approach to a surface and the boundary layer above it. But for many exoplanets in the stormiest categories, especially giants and sub-Neptunes, a solid surface may not exist at accessible depths. Instead, there can be a transition into dense fluid envelopes and, deeper still, into interiors where composition and phase can change profoundly. In this region of the topic, storms are traced to their last depth, where circulation meets deep mixing, where cloud cycles end, and where uncertainties become unavoidable because observations cannot reach these layers directly. In giant planets, the deep atmosphere is often expected to be convective over large ranges of depth. Convection establishes an adiabat, a temperature profile set by rising and sinking motions that keep the fluid near neutral buoyancy. Yet convection is not uniform. It can organize into plumes, broad upwellings, and downwellings shaped by rotation. In a rapidly rotating deep atmosphere, the flow can align into columns parallel to the rotation axis, a behavior known from rotating convection experiments and from models of gas giant interiors. These columns can support deep jets that extend downward from the visible atmosphere. Whether jets extend deeply is an active question even within the solar system, and for exoplanets it is even less constrained. It remains uncertain how far down the observable wind patterns continue, and where they fade into slower interior motion. The deepest storms, if they can be called storms, may be less about clouds and more about compositional layering and mixing. Many giant planets are expected to have gradients in composition, with heavier elements more abundant at depth. If such gradients are strong, they can inhibit convection, creating layered convection or semi-convection, where thin convective layers are separated by stable layers. This can slow heat transport and create long-lived structures. In that regime, storm-like mixing can occur in bursts when layers overturn or when shear instabilities erode boundaries. Such processes could influence a planet's radius and thermal evolution over billions of years. They could also influence the supply of condensable materials to upper layers, thus indirectly shaping cloud storms above. In sub-Neptunes, the interior structure can include a rocky core surrounded by a thick volatile envelope. The envelope may include water, ammonia, methane, and hydrogen and helium in varying proportions. At depth, pressures can push water and other volatiles into exotic phases. Water can become supercritical. It can also form high-pressure ices at certain conditions, though those phases are typically discussed for colder interiors and specific pressure-temperature paths. Regardless of exact phase, the transition from a gas-dominated outer envelope to a dense fluid interior can be smooth. In such a planet, deep circulation might connect to a boundary at the top of a dense fluid layer, where composition changes and where the ability of material to mix upward is limited. Storms above could be influenced by how easily volatiles are transported from depth to cloud-forming regions. For hot Jupiters, stellar irradiation can create a strong radiative zone that extends deep, suppressing convection over a wide range. Below that zone, convection resumes. The depth of the radiative zone depends on opacity and irradiation. If the radiative zone is deep, the upper atmosphere's storms may be largely decoupled from the interior. In that case, deep storms may be muted, and the upper winds and cloud cycles may run on stellar energy alone. If the radiative zone is shallower, coupling can be stronger, allowing interior heat and mixing to influence observable layers. The degree of coupling remains uncertain and varies by planet. This uncertainty matters because it determines whether the deepest layers are participants in storm regimes or merely slow reservoirs beneath them. At very high temperatures, molecular dissociation can occur in deep layers, changing how heat is transported. Hydrogen can dissociate into atoms and later recombine, a process that can carry energy without requiring large temperature changes, somewhat like latent heat. In extremely irradiated planets, dissociation on the day side and recombination on the night side can occur at pressures that affect atmospheric circulation. This mechanism can enhance heat transport because recombination releases energy in cooler regions. While this process is often discussed for upper and middle atmospheric layers of the hottest planets, its deepest extent depends on where temperatures and pressures cross dissociation thresholds. The storm, traced inward, becomes a chemical energy transport system as well as a fluid one. The final depth of cloud cycles depends on whether condensates can survive. Mineral and metal clouds require temperatures below condensation thresholds. At depth, temperatures rise and those condensates evaporate. Water clouds also end at depths where temperatures exceed saturation. Thus, the deepest levels are often cloud-free in the sense that condensates cannot exist. Yet the absence of clouds does not imply calm. It implies that storm energy is expressed as mixing, waves, and shear rather than as visible cloud structure. In dense layers, shear between jets and surrounding flow can create instabilities. These instabilities can mix material and generate turbulence. Turbulence can transport heat and influence how the atmosphere approaches equilibrium. At the boundary with a core, if a solid core exists, additional dynamics can arise. Heat from the core can drive upward flux. Chemical interaction between the core and envelope can release or absorb heat and can change composition. If the core is eroding into the envelope, heavy elements can be mixed upward. The extent of core erosion is uncertain and depends on materials and conditions. Some models suggest that cores in giant planets may partially dissolve into metallic hydrogen layers, enriching the envelope. For subneptunes with water-rich envelopes, interaction between core and fluid can also alter composition. These deep processes occur over long timescales, yet they can set the baseline composition that determines what clouds form above and how strong storms can be. Because direct observation cannot reach these depths, the science relies on constraints such as mass, radius, orbital properties, and the properties of the observable atmosphere. Transit and radial velocity measurements constrain bulk density, hinting at interior structure. Thermal emission and phase curves constrain energy budgets. Spectra constrain composition and cloudiness in upper layers. From these, models infer plausible deep structures. Yet multiple deep structures can fit the same data. It is therefore important to state boundaries. Observations indicate vigorous atmospheres in many exoplanets, with strong winds, clouds, and chemical patterns. It remains uncertain how these connect to the deepest layers and whether deep mixing is continuous or layered. In this inwardmost region, the strangest storms are those that turn into slow, planetary breathing. They are the deep convective motions that set an adiabat and feed waves upward. They are the compositional gradients that resist mixing and create layered overturning. They are the invisible shear zones that generate turbulence in dense air. They are, in some planets, chemical energy transport through dissociation and recombination. By the time the storm reaches this depth, it is no longer a visible event. It is a way the planet moves heat and matter between its interior and the space above. The outer layers display clouds and phase curves, The deep layers set the conditions that make those displays possible. The chain from starlight to cloud to deep mixing is continuous, yet the last links are inferred rather than seen, and uncertainty remains a necessary part of the description. The sky of a distant planet is not a silent shell. It is a moving boundary between heat and cold, between gas and condensed matter, between chemistry driven by light and chemistry driven by pressure. Some worlds carry storms made of silicate grains that form in darkness and vanish in glare. Some carry iron and other metals as vapor, then return them as precipitation on cooler sides. Some hide water clouds beneath hazes that flatten spectra, while others enter colder regimes where methane becomes both gas and ice. Across these worlds, winds reshape heat maps and shift the brightest regions away from where starlight falls. Higher up, radiation and stellar wind can swell an atmosphere until it streams outward, blurring weather into escape. Deeper down, internal heat and convection continue to stir the air long after clouds disappear from view, feeding waves and jets that reach toward the observable layers. What is measured is faint light and subtle spectral patterns, yet those signals already show that storms are common and diverse. The strangest part is not that the physics changes, but that familiar processes, circulation, condensation, mixing, and radiative balance, operate on unfamiliar materials and scales. The planets remain distant, and their storms remain partly hidden, but the evidence steadily narrows what is possible and clarifies what is active.